Welcome back to Multigrid Methods. We're in Chapter 9, talking about additive preconditioners based on subspace decompositions. So we're in slide deck 1 of 2. I think I'd love to be able to finish this slide deck today, but we'll see what happens. Last time we described what we meant by assumption SS1. So we constructed a set of prolongation matrices, and we said that those prolongation matrices supported a subspace decomposition of Rn if any U in Rn can be written as a sum which looks like this, where these Wj's are appropriately chosen. So the idea is these Wj's are chosen based on our selection of U. So you give me a U and I can give you at least one set of Wj's so that this happens. If that is the case, then we say that these prolongation matrices support a subspace decomposition of Rn. And we went through a couple of examples, one which I would consider to be the simplest example. And then I did two examples of hierarchical basis technique. And I asked you guys to have a look at that and see if you could come up with the general rule for that. The second one that we did, the second hierarchical basis decomposition, is in the same example as the first, but it's slightly different. And so it may seem like if I try to generalize the second, it's different from the first, but you can generalize them both more or less simultaneously. Where's the basis aspect for this hierarchical basis decomposition? Well, usually when we see a basis, we're thinking, well, we should be able to write a basis down where the basis elements are of the same size as the dimension of the space. But here you see what we do when we decompose things, we're decomposing based on these matrices. But really the way you should think about it is that these bases are the columns of these matrices. So the basis, all I've done is group this, we basically have one basis, one canonical basis for R23. It's E1 hat up to E23 hat. So that's our canonical basis for R23. So the hierarchical aspect of it is that we are breaking these up in certain ways, and then we can, so these matrices can be kind of stored offline, and all we really need to know about them is how we're allocating these different nodal values or these different index values. Then the basis is actually here, okay? And here you can see we're not storing any of the zeros that we would normally store for in some sort of basis decomposition for some vector. So this allows us to store U in a fairly compact way. Okay, in a basis, quote unquote, that is in R as an element from R2, R3, R6, and R12. And if I add all those things back up, you can see I've got all of the components of U in here, U1 up to U23, all the even components, all the odd components, etc. But I'm kind of storing these in a kind of weird compact way. And so this is the idea of this hierarchical basis decomposition, such that when I add these guys back up, I need to convert this back to a vector in R23. Same with this one, same with this one, same with this one. And that's what these prolongation matrices are doing. They're kind of expanding these back up in the appropriate coordinate way to give me back my original vector U. That's the idea of hierarchical basis decomposition. We're going to come back to this in a moment when we talk about the finite element method being viewed in terms of the hierarchical basis decomposition. Hierarchical basis or bases will give us an alternative structure for writing our problem to the standard Lagrange nodal basis way of writing our problems. All right, so this is new stuff from this chapter, an additive subspace preconditioner. Now, We did mention last time I got it wrong, and then one of you guys helped me figure out how to get it right. So the basic idea of creating an iterative method, which is additive, means that we can write a iterator matrix in some sort of process. So we have a standard general linear iterative scheme process, UK plus 1 equals UK plus B times F minus AUK. And basically, what we're doing is breaking our iterator into a bunch of sub-iterators. B1, I'm going to write this in a slightly different way because our subscripts here are going to mean something a little bit different. I'm going to write these as we're having superscripts. Okay, something like that. So we can break this process into an iterator matrix, which can be written as a combination of multiple iterative processes or multiple iterator matrices. And then we can break this computational step here up into a series or a system of parallel operations, which can be parallelized on the computer in the standard way. So we don't discuss parallel computing here. Some of you are familiar with parallel computing and know what I'm talking about and makes sense, and some of you are not. So don't worry too much about that. The important point here is that we're creating an iterator matrix B, although we're going to call it C down below, that can be added up in a bunch of discrete pieces. So our discrete pieces are going to come in size, or there's going to be capital L plus one of them instead of R of them. And we're going to break it up in this way. But this is just going to give us an iterator matrix, which we're going to use to our advantage later on. So let me get into the definition. Suppose that assumption, let's see here. Can you guys still hear me, or did I black out with the audio?
Still hear you.
I can hear
Okay,
you.
good. So there's something wrong with this headset. As long as I keep the power off, I should be fine though. Okay, so let's assume that assumption SS1 holds. So we've our set of prolongation matrices support a subspace decomposition for Rn. So here's that set of prolongation matrices. The matrix C is called an additive subspace preconditioner with respect to this this subspace decomposition if and only if there are SPD matrices. So I need the same number of SPD matrices as there are these prolongation matrices. There's going to be L plus one of them counting from 0 up to capital L. Each one of those CL matrices are themselves going to be symmetric positive definite. And C is going to be arranged or constructed as a sum of QL, CL inverse, ZL. QL, CL inverse, ZL, where ZL is just the transpose. This is a typo here. That should be my top symbol. Also here, top symbol. All right. So in any case, transpose. So ZL is equal to QL transpose. So this just means the adjoint in the standard Euclidean sense. Standard Euclidean sense. So I'll just remind you what it means to take a transpose or an adjoint in the standard Euclidean sense. Well, you could either permute rows and columns as you're taught in an elementary linear algebra course, or you can define it this way. When I want to bring QL over to the other side, it comes over with this object called a transposition symbol. Well, this ZL is equal to QL transpose, so ZL is what you get whenever you move QL over to the other side. Let's make sure everything makes sense. So V is in Rn, okay? V is in Rn. QL, what is the size of QL? So QL had to be, so what we want is VL, sorry, QL times V, this should be something which lives in RML, right? So we need V is in n by 1. N by 1. And what did we say Q was? Q, it should be ML by N. And I think I've gotten that wrong. So that's, I'm glad I checked that. So let's go back and see what do these Q matrices have to be? These Q matrices are actually like this, okay? They're tall and thin, tall and thin. How do I know that? Well, M or N is the largest out of these numbers, and these are smaller. So I think of this is like 7 and this is 3 or 2, something like that. So I should have put that Q on the other side, and I'm glad I checked because otherwise you just assume you're correct. So the QL should be, this is an error, right? Correct me if I'm wrong. The QL should actually be written over here because UL is in ML. So I could do QL times UL, and that would make sense, right? So this is incorrect. Should be the other way around. That guy should go there. And that guy should go over there. So we could do the multiplication QL times UL. That should make sense because this is going to be N times M sub L, and this is M sub L by 1. So that gives me a result, which is going to be some vector W, which is going to be N by 1. Okay, so I have it wrong here. The other mistake is that that should be L there, no L there, and then I put L here and here. Okay, so I'll fix that up. So the way it should be is the following. It should be QLUL V. So the result is in Rn. So for Rn, I'm not going to put any symbol down there. When I move it over to the other side, I have UL QL transpose times V. And when I do that, I'm going to put an L symbol. Remember, if these things are not square, QL is not square, then I have to ratchet the size of my inner products. Now this thing ultimately is equal to UL ZL V. And I think that is now correct. That's what it should have been. So as it's written, not correct. But in any case, I was just trying to make it clear what I meant by the transpose, but if you write the wrong thing, then it's certainly not clear anymore. Okay. Now, I want to point out that in all of the computations that follow, I'm going to use the same notation. An inner product with no symbol down below, that means the standard Euclidean inner product on Rn. So just dot product. And if I have a subscript L, that represents the standard Euclidean inner product on RML from L equals 0 up to capital L. Similarly, if I have a norm, that just means Euclidean norm, as long as there's no subscript. And if I have a subscript, it's usually the Euclidean norm, or at least it always is in this case. It's the standard Euclidean norm, the 2 norm on RML. Okay, for L equals 0 up to capital L. So just keep that in mind as you look at these and you see, oh, what does this inner product represent? If it doesn't have any symbol, it's the inner product standard 1, standard Euclidean inner product in Rn. All right, suppose that assumption SS1 holds, that we have the QL matrices, these prolongation matrices, support a subspace decomposition of Rn. And suppose that C is an additive preconditioner with respect to this family. Then this C matrix is actually SPD with respect to the standard Euclidean inner product on Rn. And consequently, if A is the matrix that we our standard stiffness matrix, although I haven't introduced it as a stiffness matrix, and we can think about it in a more general context here. If A is some SPD matrix with respect to this inner product, that means it's an R n by n matrix, and it's has the usual properties of symmetry and positive definiteness. Then C times A is SPD with respect to either this inner product or that inner product. Actually, it's SPD with respect to both of those. Now this part, if we know that C is an SPD matrix with respect to that inner product, then we've already proven this in chapter 1. So this part here is taken care of by a result we had in chapter 1. What's new is showing that C is itself an SPD matrix with respect to Rn. That's what we want to show. That's the key missing piece. Okay, so now C is a sum of a bunch of matrices which turn out to be each one of them symmetric. That's because each CL inverse is symmetric. If CL is symmetric, positive definite, then CL inverse is symmetric, positive definite. The key term we're going to use here to begin with is symmetry. So if you remember how C was defined in terms of these C inverse matrices going back to the definition, so this whole thing is a symmetric matrix on account of the fact that I'm using QL and QL transpose on either side of this sum, these individual summands. So this means that C, by definition, has to be a symmetric matrix. Now, let's let U be an arbitrary vector in Rn. So we want to show that this bilinear form, or this quadratic form here, is a positive quadratic form. I call it quadratic because whenever I take U against itself in some sort of inner product, it's a positive quadratic function as long as this C matrix here is a symmetric positive definite. And it's just another typo. That should be an MSF format. Just a little it's a typesetting typo, not an error otherwise. So, by the way, if in the book you see something like this, I would love to see that, or love for you to tell me about it. See how this C is a little bit more upright and this one is slanted? That tells me that I used the wrong font for that guy. So that's when you see I'm making little notes like this on typo or a typesetting error, that's because I forgot to set that in the proper font. In any case, I'm sure some of you care and some of you don't. Now I'm just going to put in the definition of C now. That's all of this guy. That's the definition of C. I want to show that this is a positive quadratic form. And what can we do now? Well, we're in the Euclidean inner product. And so Euclidean inner product is an inner product, and so it's bilinear. It's linear in the first and the second components. We'll use the linearity in the second component to pull this guy out, this sum. So we just get that. And now I'm going to throw this QL over to the other side. When I throw the QL to the other side, it becomes a ZL, and I have to switch from Rn space to RML space. Okay, so bottom line is I've got to add this subscript L. Now, each one of these quadratic forms here turns out to be a positive quadratic form, or at least a non-negative quadratic form. And that's because I know that this guy is SPD. And so this is like an SPD with the same vector appearing in both locations. In fact, I can pull this guy out down to here, and I could use that as my inner product. In any case, I know that this is going to be greater, each one of these is going to be greater than or equal to 0 for each L. So that tells me that the whole sum is greater than or equal to 0. By the way, this is another typo I want to fix. So this should be down on another line. Okay. Now, I just said that. So since CL is itself SPD with respect to this inner product, we know that each one of these forms is greater than or equal to 0. Now it's going to be positive if we can find out that ZLU is a positive, is itself a vector which is, let's see, how do I want to, so what I want to argue is that this is going to be positive because since U, if U is not 0, then ZLU is not going to be 0 either. Okay. Now I want to suppose, let's see then what happens if each one of these guys, or if the sum of these guys is equal to 0. I want to show what that means is that U is going to be equal to 0. And if I do that, then that gives me my positive definiteness. So let's go ahead and set this equal to 0. So that's the sum of each one of these summands is equal to 0. Now, CL inverse is SPD. So what does that mean? That means that each one of these guys, if these are all greater than or equal to 0, so be careful about the argument. Each one of these is greater than or equal to 0, and their sum adds up to be equal to 0. That means each element in the sum, or each summand, has to be itself equal to 0. But CL inverse is SPD, and the only way that that can happen is if each one of these vectors contained in here has to be equal to 0. Okay, so this assumption leads to this result. ZLU is equal to 0 for each L between 0 and capital L. So now I just have to prove that that means that the only way that this can happen is if U is equal to 0. So let's see. All right. So let's have a look at, let's include that in some sort of writing of U. So let's look at the norm of U squared. So the norm of U squared, of course, is just equal to the inner product of U against itself. All right, so we have U, and I can write U using the fact that I have a subspace decomposition, or in other words, since QL supports, the set of QL supports a subspace decomposition of Rn, I know that I'm able to write U as a sum which looks like this. For some WL, okay, for some WL collection. That's because I have a subspace decomposition. Now I can use the linearity of this inner product to pull this sum out front. I get this. I can throw this QL to the other side to get a ZL. ZL against WL, right? I don't know what these WLs are, but I don't care. But now I know that CL is equal to 0 because of this conclusion here from 3. So I can put 0 there. Each one of these has to be equal to 0 because I'm taking the inner product of WL with 0. That gives 0. So I've just shown that that must mean that U is equal to 0. Okay, so because if the norm of U is equal to 0, the only way that can happen is if U is equal to the 0 vector. So we've shown it in 2 steps. We first showed that this form was greater than or equal to 0. And then we argued that the only way that that can be equal to 0 is if U is itself equal to 0. That means that this C has to be a symmetric positive definite matrix with respect to the Euclidean inner product. The second result, that CA is symmetric positive definite. So a product of 2 symmetric matrices is not even necessarily symmetric in the Euclidean inner product. So you have to go to another inner product if you want to make such a claim. Well, it turns out if I go to this inner product or this inner product, it happens to be true in both, that CA, this product, is SPD in both. And that was a very easy proof that you guys did way back in chapter 1. So that we get for free.
Dr. Wise, why the small l starts from 1, not from 0 in the previous?
Oh, that's a typo. Thank you. Typo. Should be 0. Thank you. Let's see if we made the same mistake anywhere else. Probably, but at least we caught it in that instance. Thank you. All right. Yeah, we're going to check. I don't know why it's done, but it's just by some sort of convention that when we use multigrid, we start counting from level 0 up to level some capital L. And so we're always going to be, or at least a lot of times when we're dealing with level dependent things, dependent operations and operators, we always start from 0. It's just a strange thing. Okay, suppose that our prolongation matrix set of prolongation matrices support a subspace decomposition for Rn. So that means SS1, assumption SS1 holds. Then we're going to write, see, do I have? Ah, this is a, yeah, I forgot to replace this with a better definition that I have in the lecture notes. So I'm going to give you, I'll give you the definition that's in the lecture notes because that's much, much cleaner and better, I think. So you can, this is kind of true, but I don't like this kind of backwards way of defining this. So, okay, so we're going to call Q U the Q class of the vector U. If you give me, if you give me this set of vectors and U, if you fix those, then I'm going to define something called the Q class. So the Q class is going to be those set of W vectors. Let's see, I'll use J because I'm using J up above. And I'm not using a set notation here. I'm using a sequence or parentheses notation here. So I don't know if it makes too much of a difference, but that's what I'm doing. I'm going to choose the set of vectors such that U can be written as J equals 0 to L QJ WJ. And I guess that we could add where each one of these guys comes from. So WJ, each one of those guys is in RMJ. Okay. And U is equal to this sum. Now here's the idea. If I have a decomposition, a subspace decomposition, then there may be a lot of different ways that I can write this U vector as a sum which looks like this. If you tell me what the Q prolongation matrices are, there could be a lot of different ways of writing U as this sum which looks like this. Now, if there's only one way to do that, if it's completely unique, and it turns out if I use a hierarchical basis methodology, it's always going to be a unique way. That means there's only going to be one element in the Q class. So this guy here is called the Q class of U. Again, think about it like this. I'm given these prolongation matrices, and I'm given U. If these support a subspace decomposition of Rn, that is to say assumption SS1 holds, then I'm always going to be able to break any U into a sum like this. Now, if you give me U, I'm asking for, in this definition of the Q class, the set of all possible breakdowns of these vectors Wj, such that I can get U to be written as a sum which looks like that. Okay? So again, if there's only one way, then there's only one element in here. But at least I know this set, this Q class of U, always contains at least one element. But it could contain a lot more elements. It could be an infinite number of elements. In fact, I think the way it goes is either it's unique or it's non-unique. In the non-unique case, there's an infinite number of ways of doing this writing. Okay, so this is what we call the Q class. And I have a better definition in the notes, and I forgot to update it in the lecture slides. So I will do for our next lesson, but if you are a little bit confused by this definition, which I don't like, I prefer the one that uses set builder notation, and that's the one I included in the lecture notes. So go there and have a look at that. So I hope you all understand this concept of Q class. It's given these matrices Q and given U, I'm looking for all the ways or all the sets of vectors such that I can write U in a sum which looks like this. Now notice the reason why I didn't want to use a set notation is because that usually assumes that each one of the elements comes from the same set, which they don't in this case. And that's because each one of these vectors, Wj, could be of a different size, right? They don't all have to be of the same size. If Mj is different for every j equals 0 to, what was j index? J is equal to 0 up to L. If M is different for each Mj is different for each one, then each one of these guys has a different size. So it's like making a collection of a vector that has length 1, then 2, then 5, then 7, etc. It doesn't really make sense to use the set notation in that case. So I opted to use the parentheses instead. Okay, suppose that assumption SS1 holds. We have a subspace decomposition involving these prolongation matrices, and suppose that C is a preconditioner with respect to this family. So we gave the definition, and then of course we showed that if C is a preconditioner, then it's a SPD matrix. Then for any U in Rn, U measured in the C inverse inner product. Remember, C we now know is SPD, so C inverse is also going to be SPD. Then we can say that U in this inner product is equal to the minimum over all WL in the Q class of U, sum L equals 0 to L, capital L, CL, WL, WL in the L inner product. Okay, this is weird. I understand. What does this mean? What does this object here mean? Well, all right, so this object here means the set of all ways of writing U. So I'm looking for all WL such that U can be written as a sum, L equals 0, or you can do J equals 0, doesn't matter. That's just a dummy index. Q, L, WL. So I'm looking for the collection of all of these guys. Okay, I'm minimizing over all such collections. So that's W in this Q class. And this sum here, what does it involve? Well, this is a part, right? This is a part of the definition of the C inverse matrix. Let me see if I can get the C matrix defined correctly. So it was sum L equals 0 to capital L, and I think was QL CL inverse ZL. Let's see if everything makes sense in terms of dimensions. So this is N by ML. This is ML by ML, and is each one of these CLs is symmetric positive definite. So I know that its inverse is, and then finally this has ML rows and N columns. So this whole thing is in N by N. I sum them all up and I get this object in N by N. So everything makes sense. So these guys are in the definition of the C matrix. But notice that I'm asking the question involving C inverse here and CL here. But in this definition down here, it's C and CL inverse. So kind of flip-flop the roles. So why is this going to be so important? It's going to be important for one of the calculations that we're going to do shortly. So we'll get on to that. How can we prove such a statement? Well, let's start by just looking at this on the left-hand side and writing out everything that we know and seeing how far we can get. All right, so if we look at this object here, it involves objects which look like that. So let's start off with that object. Since each CL is SPD, with respect to that inner product, we know that this object here is a bona fide inner product. Bona fide means good and true inner product. So by definition, this object equals this object here. That's by definition of what we mean by this inner product. Now, since this is an inner product, let's see, I want to make a correction here. Just eliminate that. Okay, I don't need that extra define symbol. All right, so since this is an inner product, we can use the Cauchy-Schwarz on this inner product. So I'm going to do the usual thing that we do, and we define a norm from an inner product by taking the square root of the inner product of an object with itself. So satisfy the Cauchy-Schwarz, and so that means that this is less than this norm times that norm, which by definition is equal to that times that, which is what I just said. Okay, that's true for any UL and any VL and RML. Now let's let U be arbitrary. Then we know that U can be written, because we have a subspace decomposition, as a sum QL WL for any WL in the Q class of U. There can be a lot of ways of writing this. There might only be one way. That's a kind of a rarity whenever you have a uniqueness. More generally, the way we made this definition, this could allow a bunch of different ways of writing this sum. So we're going to stick with that. We're going to stick with the assumption that there is at least one thing in there, but there could be possibly an infinite number of things in there. And now, as I said, we're interested in computing that thing on the left-hand side, which we originally had. We want to show that this is the first. We're going to do this in two steps. We're first going to show that this is less than or equal to sum, which is like this, for sum or for any WL in the Q class. And then finally, we're going to minimize over that Q class. So let's start with the object on the left. And because we have subspace decomposition, we can write U, the second entry in this inner product, using that subspace decomposition. And then we're simultaneously going to pull the sum out using the linearity of this inner product. Next step, I'm doing multiple steps at once. I'm going to pull this, no, that's okay. That's good. That's okay. I'm going to pull this C inverse out, and I'm going to throw it onto this U. Okay, for each L, I'm going to pull that out. So that C inverse lands on there. And when I do that, that results in switching to the Euclidean inner product here. But then I simultaneously move this QL over to the other side, and it becomes a ZL because we're in the Euclidean inner product. That changes the inner product from an inner product on Rn to an inner product on level L. Okay, so I did a couple of steps there at once, and it's an exercise to see if you can get from one step to the next. Going from there to there, right, is an exercise. Okay, now what do we want to do next? Next step is to, let's see. So here I have ZLC inverse UWL, right? Here I'm going to multiply, well, let's say take that point there, multiply by CL inverse times CL. That just gives the identity. CL inverse times CL. And then we're going to pull the CL inverse out as to make an inner product. Okay, so here I had CL inverse times CL, but that's just the identity. And then I pulled the CL inverse out. Okay, otherwise it stays the same. Now, once again, I'm working in the CL inverse inner product, and that's a bona fide inner product for each L. So I'm going to use the Cauchy-Schwarz inequality, just like I did before. I'll break this guy. I'll break this guy into the product of two inner products. Okay. So that's the Cauchy-Schwarz for an inner product. Cauchy-Schwarz for an inner product. And notice that I'm doing that for each L going from 0 to capital L. So Cauchy-Schwarz just for each inner product is going to yield this, which I described earlier. Okay, this vector goes here. This vector goes here. Okay, I did Cauchy-Schwarz for this inner product. Now, look at this. This looks like a usual inner product of something, right? This just looks like a dot product on some space. In fact, it's on what space would it be? This is like a dot product on R L plus 1, right? Because there are L plus 1 components. This is like AL times BL. That's just a usual Euclidean inner product when I have a number here and a number here, each dependent upon L, and then sum L equals 0 to capital L. So now I'm going to use the Cauchy-Schwarz on this space with this inner product. I hope you see that. Okay. If I do that, then I'm going to take the square root of the sum of each one of these indices, or each one of these components squared. Now, the fact that this is a norm means that this becomes a norm squared, and same here. So if I square those components for each L, then I get the norm squared, sum from L equals 0 to capital L. So this is actually Cauchy-Schwarz on RL plus 1. Okay, now I'm just going to convert these objects here from this norm squared into an inner product. So each one of these gets converted into an inner product. It's the same inner product because it's the same norm. Okay, so ZLC inverse U, ZLC inverse U, CLW, CLW. All right, now here you can see I can move this guy up to one of these guys and I could create the identity if I want. And that's exactly what I did. I created the identity on the right-hand side by moving that CL inverse up, and it attacks the CL. CL inverse times CL gives the identity. So that's just identity there. This guy here, I did the same thing, only it doesn't create an identity matrix. I'm moving this, I can move to this position or that position, and then this changes that to an L. So I decided to move it on to the right-hand side, change that inner product to an L. Okay, now, if I look at the definition of C, so this is a little exercise that I don't want to spend our time now. So this is exercise to see if you understand that if I use the definition of C, remember C involves ZLs and QLs and CL inverses, then this object here is going to turn into this object. So I'll let you guys do that calculation. I guess I could have, I don't need this extra parentheses here. That's a little bit redundant. Redundant. I can just put a square root on that if I want to, but I don't need the extra set of parentheses. What else? This guy here, I didn't do anything to that, right? Just left that alone. Now, C times C inverse, that just is the identity. So it goes away. And then I just have C inverse U in the Rn inner product. So that's just another way of saying I have a square root, right? So this becomes the C inverse inner product, but with a square C inverse inner product square root, that's just the C inverse norm of U. That's because the same object appears on the right and the left-hand side. Nothing changes here. Now, the thing I started with in this last calculation was this, but that's just the norm of U in the C inverse metric squared. So I can use the cancellation property to cancel one of those guys, right? So this is norm C inverse squared. Now you can't use the cancellation property if U is already equal to 0. So to use cancellation, you've got to say, I'm going to assume that U is not equal to 0. But if it's equal to 0, I'm going to end up with a triviality to begin with. Okay, so cancellation is possible as long as I assume that U is not equal to 0. Then I'm going to, once I cancel this, then I'm going to square both sides. And so the thing which was a norm becomes back to an inner product, and this square root goes away. Okay, so when I square both sides, I end up with this. Now this holds for all WL in the Q class. So it didn't matter what WL I used. If WL was unique, then I'm done already. Well, I'm not quite done, but there would only be one element in the Q class. There's only one way of writing it. Now, in general, the Q class, as I said, it either has one element or an infinite number. We're not going to assume that it has a single element. In other words, we're not going to assume that Q supports a unique subspace decomposition. Let's assume that there could be an awful lot of elements in there. So now we can take the infimum over the set of all these numbers, right? So this is an upper bound. And if we take the infimum over all W's, this upper bound is an upper bound for the least upper bound, which is what the infimum is. All right, but so that still produces an inequality. I've got to show equality in order to complete this, right? So what I can show here right away is U C inverse is less than the infimum of all WL in the Q class of all objects which look like this. L equals 0 to L. So these are a bunch of numbers. So I'm taking the infimum over a bunch of numbers. In fact, you can only take the infimum over a bunch of numbers. So keep that in mind. But I still have some sort of gap here, right? I want to show actually that this infimum is attained, and it's attained at this value, in which case I can replace this infimum by a minimum. Well, the way to do this is to show or to pick some sort of specific value for the WLs. And the one I'm going to use is precisely equal to this one. So I've set this up as an exercise. I want you guys to prove this. But what I want to check here in class is, let's make sure that each one of these WLs is an RML. Well, this starts out in Rn. I multiply by an n by n matrix, still an Rn. Multiply by a matrix which is ML by n. So this vector here is in ML. And then I multiply by a matrix which is ML by ML. So the whole thing then is in ML. We're good to go there. So that I like to, the nice thing about working in this matrix way is we should always be able to compute and find out whether an object at least makes sense. And this, for me, this is very helpful for learning this theory. Just making sure that an object lives in the space that you say it lives in. That is a kind of zeroth order analysis that I always like to do. But it's an exercise to show that if I choose these WLs in this way, then I actually, these WLs are in the Q class of U, or the sequence of these WLs is in the Q class of U, meaning that I can write U as this sum. So that's an exercise to show that, but not a hard one. So, okay, so if that's true, what we want to do is, right, we've got this guy over here. We want to show actually that with this particular choice of W, I actually get back to that value, and that'll show it. So start with that value. I want to show that through some work, I get all the way back down to here, and therefore I've shown that the infimum is attained, and it's attained at UU in the C inverse inner product. All right, so let's plop in let's see. So how do we do this? So I'm going to plop in this definition for WL and WL. So there and there for each WL. Now let's see, we get some nice cancellation, right? Right off the bat. I can move this guy to the other side here. So that's going to become a QL, right? And all I'll be left with over here is just C inverse U. I'm going to shift from the L inner product to the N inner product, or the base level, or the RN inner product. This object here is just my definition. If I bring this guy in, because this is now independent of L, the only L dependence is here, but when I bring that sum in, this just defines C. All right, so I have C now against C inverse. Of course, I get the identity there, and or you could bring this guy if you wanted to do an extra step. Since this is a symmetric positive definite, bring that over. C times C inverse, you get the identity there. Doesn't matter how you do it. It's all the same, because all I'm going to be left with when I cancel one of those is a C inverse, which I can bring out in order to form a C inverse inner product. So I just showed that the infimum is attained, and therefore I'm done. All right, now let's think about what the heck does this mean? What does this mean? So U against U in the inverse inner product, C inverse inner product, is minimized when I take the minimum over all WL in the Q class of objects which look like that. So it's hard for me to put that into a picture. I don't know exactly. I can't give you a simple explanation of what that means. But we know, at least with our analysis, that it's true. So we're going to just have to hope for now that this object becomes useful. And in fact, it becomes useful pretty quickly, as we'll see. All right, now we're gonna write a formula which looks crazy complicated, but which turns out to be pretty simple, actually. And that's because the object that we're going to replace, which used to live down here, we can replace with this min, because we just proved this object here. We just showed that what object can this replace? Well, we just showed that this is U against U, C inverse inner product. And same here. Here and here. Same. Well, it turns out if I get rid of this awful looking mess here and I write that, that's just going to be a simple identity. And it's based on essentially the Rayleigh quotient, which we've seen before. Same here. This one is going to be based on the Rayleigh quotient. Now, where does this come? Well, this is a property involving Rayleigh quotient, which we'll see. Suppose that assumption SS1 holds, or in other words, the set of prolongation matrices form or support a subspace decomposition for Rn. Suppose that C is a preconditioner matrix with respect to that, then the eigenvalues Ca are positive, great, provided A is SPD with respect to this inner product. Furthermore, the maximum eigenvalue of that product is equal to this crazy looking formula, the max over this. And again, these are just like Rayleigh quotients. And the minimum eigenvalue is the min over the Rayleigh quotients. Actually, that part is just known to us already. It's the fact that we're making this replacement, which gives us this simple looking, well, no, this complex looking identity, which is just involving a simple replacement. Okay, so recall that a product of two symmetric positive definite matrices, as we have here, is symmetric with respect to, got a typo here, no period. No period required with respect to either this inner product or the A inner product. Doesn't matter which one you use, it's true for both. So the eigenvalues are positive and the corresponding eigenvectors be chosen to form an orthonormal basis for Rn with respect to, what the heck am I doing here? I like to put periods after the word to, I guess. Actually, this is probably my former students typing here. So I'll take the blame, but it was probably someone else. Okay, so moreover, the Rayleigh quotient formula holds. So the Rayleigh quotient formula is going to tell us right away that the maximum eigenvalue is equal to this over that, where I take the maximum over u in Rn star. Why is this? Why does the Rayleigh quotient formula tell us this? Well, this is just Rayleigh quotient. We're using the fact that this is SPD and this inner product, so that's why we're using that inner product. That is the coefficient matrix that we're interested in, the product of C times A. So that goes there. So that's just a Rayleigh quotient. So we know that if we maximize the Rayleigh quotient over all u not equal to the zero vector, then we get the maximum eigenvalue, period, full stop. And now we're just going to replace this guy with the minimum taken over all the WLs in the Q class of objects which look like that. So I don't know why it's important. At least we don't know why yet, but that's how it works out. Now, if I want to find the maximum eigenvalue for C times A, the minimum eigenvalue, I minimize over that. Okay, minimize over these numbers. Where u is not equal to the zero vector. So I get the same formula essentially, only this is replaced with a min, and I replace this by the thing I just proved, and you get the formula that you want. So min and min, or max with min. Okay, so those are the two Rayleigh quotient formulas that I need, and basically everything that I've computed up to this point was getting these formula here for 5 and 6. It's going to turn out to be quite essential for the analysis that we want to do when we start talking about hierarchical basis in the finite element setting. The next topic we want to talk about are hierarchical bases constructed from the finite element viewpoint. So I've given a kind of abstract way of looking this as just a way of decomposing Rn. But now I think you'll see how this comes out of finite element setting, if that is, if I do my job correctly. So remember, we had this object or this idea called the Lagrange nodal bases, right? And so we used BL to denote those guys. So now I'm going to put an extra little piece of notation on it if we use the standard Lagrange nodal basis, and I'll get to that in a minute. Because it turns out there's lots of different bases you could use for this finite element setting, just like there's lots of different bases for Rn. The canonical basis is a good one to start with, but it's not the only one that you have to ever use. So we're going to look at that particular hierarchical basis decomposition that's going to help us break the subspace in the finite element subspace up in new and interesting ways. But let's think about how did we do refinement in the finite element setting? Well, we only really explained it in d equals 1 and d equals 2, 1 dimension or 2 dimension. So if we're in 1 dimension, what do we do for refinement? So all we did is we took a triangle in 1 dimension. Triangle in 1 dimension is just a line or an interval, and we bisected it, right? We bisected it by putting something, a new point in there. So now we get 2 new triangles out in the end. So actually, this isn't right. I should maybe move this over. So this is now 1 element, and this is its neighbor element or brother or sister element, right? So 1 parent element gives rise to child elements or daughter elements. Now, if we're in 2D, we have the parent element is an actual triangle, even though I'll say triangle in any dimension, whether I'm working in 3 dimensions or 4 dimensions or whatever. in general, sometimes we use the term simplex. In any case, I'll just call it simplex a triangle. So now if we have a triangulation in d equals 2, then we break that up into a bunch of smaller triangles, actual triangles. And how do we form daughter triangles from this parent? Well, we're going to quadrisect this by taking the midpoints and joining them together. Okay, and that gives rise to this. So the parent gives rise to 4 daughter elements. So probably should take this guy and move it into one of these guys, because instead of having one new element, we actually have 4. And in this case, instead of having one new element, we have 2 new elements. Okay, so suppose that D is equal to either 1 or 2. It's a little bit harder to envisage in 3 dimensions. And suppose that omega is an open interval or an open convex polygonal domain in D equals 2. Suppose that T naught is an initial conforming partition of uh, in D equals 1, or a triangulation. I guess I called it partition in D equals 1 and triangulation in D equals 2. I'm going to go back and check to make sure I did that. Did I really use partition? I think I used triangulation for both cases, but I'll go back and check just for consistency. But anyway, suppose that I break this interval of 1 in 1D up into a bunch of triangles, or take my original polygonal domain in 2D and break it up into a bunch of triangles. Either way, it can always be done. Let TL be a family of triangulations obtained by doing this subdivision, right? So if we keep subdividing, right, we get a family, a hierarchical family, or a nested family of triangulations in the usual way. So this is what we explained in chapter 6. The way we're going to do it in 1D is we break into 2 equal subintervals. Each interval in 1D gets broken up into 2 subintervals, or each triangle K in a coarse mesh gets broken into 4 similar triangles by joining the edge midpoints in 2D. So exactly like I showed here in figure 1. This figure reference shouldn't be there, so that's a typo. You'll notice then when you use Beamer, it doesn't actually put figure numbers, so it's no point putting figure references. Even though Beamer will happily reference figure 1, there is no such thing as figure 1. It's just figure on the previous page. Okay, so let's set VL to be equal to the set of all functions that are globally continuous, such that when we restrict V to triangle K in the mesh, then we have a linear object, okay, a linear function for every K in the triangulation. I think I might need maybe a space there. And we're going to use the usual idea that V should be equal to 0 on the boundary. All right, so suppose that NL is equal to the dimension of this space. So we're going to set W0 equal to V0. So I have some Lagrange nodal basis, or sorry, I don't want to get there yet. So yeah, just hold on for that a second. If we're all the way at the base triangulation, I'm trying to define these new spaces called these W spaces, WL spaces. If I'm at L equals 0, I'm just going to define W0 to be V0. So this is defined for all L, all possible L's, from L equals 0 all the way up to capital L. Fine and dandy. On level 0, I'm going to set W0 to be equal to V0. But I'm going to do something different for each higher level. And I'll show you 3 examples what's going on here. So this gives us a firm analytical algebraic definition, but I can show you geometrically what's happening here, but you just have to wait and see for just a second. So I'm going to take WL to be the set of all V and VL such that V at certain nodes are equal to 0 for all j between 1 and nl minus 1. Now, what nodes am I going to use? So these are the set of nodes, but at the lower level. So this is level L. I'm going to look at the nodes on level L minus 1. I'm going to demand V has to be equal to 0 at all those nodes on the previous level, or the level, the course level just below me. For all j between 1 and nl minus 1. So all nodes in the course mesh. All right, so recall that these are the nodal sets, and they're indexed by L and J. So remember, if I have a mesh in one dimension, so for level 0, I might have only one interior node, but at level 2, I have 3 interior nodes, and at level, oops, I got that wrong. Let's start over again. So that's level 0. Level 0, level 1 has 3 interior nodes, and level 2 has 1, 2, 3, 4, 5, 6, 7. Okay? So these nodes are stored up in this nodal set. And each level has a different nodal set, but notice, let's color these guys. Let's color them. So there's the level 0 node. When we go to level 1, then that's going to add 2 nodes, but it's also going to retain this middle node. Now let's go to the next level. So that's going to be level 2, and we're going to add 1, 2, 3, 4 nodes. So you can see that the level 4 collection of nodes contains, sorry, level 4. Okay, so 0, 1, and 2. Level 2 collection of nodes, I added these guys to get the level 2 collection of nodes, but all of these nodes are in level 2. It's just that level 2 nodes happen to contain level 1 nodes and also level 0 nodes. And you can probably see, if you were interested in that little problem I gave you earlier, hierarchical basis decomposition, how things are coming together, and this is related to hierarchical bases. Now, in any case, I can store up these nodes in this set builder way, but notice that these level L nodes contain some nodes which were in level L minus 1, and they even contain some nodes in level L minus 2, and so on all the way down. Okay, now let's have a thought just for a minute. What is the dimension of this space? What would be the dimension of that space? Well, it's certainly not the dimension of this space, because I'm nullifying certain values of V at certain nodes. All right, so these force these out from being degrees of freedom in WL. So this means that WL has a dimension which is strictly smaller than VL. Okay, we're going to set ML to be the dimension of WL, and then we're going to figure out what that value is going to be momentarily. But we know that it has to be less than or equal to, well, actually, we know that it's got to be less than NL, right? By BLV, we're going to denote the family of Lagrange nodal basis elements on level L. So that's the collection of Lagrange nodal basis elements. Remember, what was the property of these guys? So these were, with respect to the nodes NLI, are equal to delta ij. Psi Lj NLI is equal to delta ij. This is the Kronecker delta symbol. In other words, if I have this, then these basis elements are 1 and 0. they're 1. This guy here is 1 at this node, and it's 0 at all other nodes. And this guy is 1 at this node and 0 for all other nodes. All right, so that's a way of characterizing what this nodal basis function looks like. Now, even though if I characterize it at nodes, it is a function. Now we're going to try to come up with a basis for W, and we're going to give that a different name. We're going to give that another definition. So I've added the V here because I'm using the usual Lagrange nodal basis elements for VL. So that gets the V. All right, but now let's look at a sample function to figure out what would be the basis for WL. Let's look at a sample function for WL. So what WL are we looking at here? Well, it depends on where we start counting. But let's see, if this is 0 to 1, then this is going to be level 1, or level 0 has 1 element, and level 2 has 3 elements, and level 2 has 7. Okay, again, level 1 has 1. Sorry, level 0 has 1. Ah, gosh, keep messing that up. L and L. So 0, there's only 1 node. Level 1, how many nodes are there? There's 3. 2, there's going to be 7. Okay. Now, what are we looking at here? This is going to be W2. W2. So the way we think about W2 is normally V2 has 7 degrees of freedom. Okay, it has degrees of freedom at each one of these nodes, but WL does not. WL does not have degrees of freedom at each node, because what I do is I take every node in the level 1 mesh. There are 3 of those, and I'm going to force it to be 0 at those nodes. So at these 3 nodes, I'm going to force my functions to be 0. So the dimension is no longer 7 for W2. It's going to be 7 minus 3 because I punched out 3 of those nodes. All right, so let's see. Is the dimension 4? 7 minus 3. 1, 2, 3, 4. Those are the only places where it can actually have non-trivial values. So we've got to come up with a basis which has dimension, or has 4 elements in it. So which ones should we use? All right, so keep in mind, if L is equal to 2, we're punching out the elements, the degrees of freedom, at the nodes which exist in level 1. So L minus 1. So that means on these 3 nodes, we're zeroing that function out. Okay, so now we want to prove, so we're going to have to wait till the next time to do this, that VL can be decomposed as VL minus 1 plus WL. In other words, VL, the difference between VL and VL minus 1 is the addition of this new space of degrees of freedom. And this kind of makes sense, right? So how do I get from VL minus 1 to VL? I take VL minus 1 and I add some new degrees of freedom. And the degrees of freedom that I'm adding are precisely going to be those ones which were not in VL minus 1, but are in WL. So VL, we can show, is just this direct sum of VL minus 1 and WL. But that's going to have to wait till next time since we're out of time. And then we'll also show that if we're at L equals capital L, then we can use this decomposition that we know here sort of recursively, and we can show that VL is equal to W0 direct sum with W1 all the way to direct sum WL. So these 2 things we'll start with next time and show. And I'm going to end there, and I'll take any questions you guys have.